Hopefully everybody managed to watch the lecture that I posted on Wednesday. I'm sorry about the internet crash. It was very unfortunate. So we're just going to continue where that lecture left off. Just as a quick recap, we talked about how the work energy theorem can be converted into an energy conservation type theorem, basically by rewriting the total work done on a system as the sum of the work done by internal conservative forces, by internal non-conservative forces, and by external forces. Then we shifted all of the external forces over to the other side, over to one side of the work energy theorem, and put all the internal forces on the other side, renamed the internal conservative forces as negative potential energy, renamed the internal non-conservative forces as negative thermal energy, and we ended up with something that looks like this. Work external equals change in kinetic energy plus change in potential energy plus change in thermal energy. So that's where we ended up with last time. And I believe I also gave an example. Let me just make sure that I actually talked about one. Yeah, for example, throwing a rock vertically is a simple example. I'm going to give another example, though, of how we can use this energy conservation to help us out. And this uses, by the way, the potential energy function for gravity, which let me just summarize. So the potential energy function for gravity as a function of, say, vertical position, where y is upwards and x is across, say, this is just mgy plus perhaps plus u naught. That u naught can be anything, and I mentioned why that can be the case in the recorded lecture on Wednesday. Right, so we're going to use this feature to solve an otherwise tricky problem. So imagine that we have a car going around a loop. And we're going to assume that there's no friction. So the scenario that we have is we have our track, we have our loop, and we have our little car. So assuming it's a box. And let's say it starts off at some position YA. We might be interested in the speed. Oh, and it's moving at some speed initially. But VA. We might be interested in the speed of the car as it goes around the loop at some other position, say YB, at some other height, YB. And we'll call that our after case. So when we do energy conservation type problems, it's useful to break up the information into a before and an after, because energy conservation is all about changes in things, delta KE, delta P, delta E thermal. And so a change means that you have a final minus an initial. So that's why we need to do this. So if we assume there's no friction, then there's no non-conservative forces. The only forces that could be present are normal forces, and those never contribute to work, and gravity. So all we have, so using this energy conservation equation, there are no external works. There's a change in kinetic energy, and then there's a change in gravitational potential energy, and there's no change in thermal energy because there's no friction. So we know that the change in gravitational potential energy, that's just the final gravitational potential energy, mgyb, minus the initial gravitational potential energy, mgya. Now, by the way, I could have added and subtracted that u naught. Which part? I could have added and subtracted that u naught, but it would have just canceled, right? So I'm just not going to do that, and that's one of the reasons why it actually doesn't matter. Why it doesn't matter if we add some constant. Right, so this is the change in gravitational potential energy. So what we get is that 0 is equal to delta KE plus mgyb minus mgya. And now we're going to use what we know about the change in kinetic energy. The change in kinetic energy is 1/2 mvb squared minus 1/2 mva squared. And then we have plus mgyb minus mgya. And now, if you really wanted to know the speed at height YB, Now there's one variable, everything else is given, ya is given, yb is given, and ya is given. Now it's just a matter of doing algebra, and so we would find, because this is all equal to 0, we would find that VB is equal to big old calculation 2m over, or 2 over m times 1/2 mva squared plus mgya minus mgyb. This is not tricky algebra, I just moved everything over to the other side, multiplied by 2, divided by m, and took the square root. But there's a change in kinetic energy and potential energy. Yes, using conservation equations, there's no work, but there's a change in kinetic energy and potential energy. Right. That's the whole point. There's no external work that's being done, because our system consists of our car and the Earth. And so the Earth, so the gravitational energy is considered internal work. And so we can simplify this, and we get that this is the square root of VA squared. Yes. Minus 2g times yb minus ya. And that just is the final speed. Now, one reason why we might be interested in this is we might say, oh, well, we know the minimum speed that this, or sorry, we know we could use this to find the speed of the car at the top of the loop, and that would that could inform us on the centripetal acceleration that it must be experiencing and so on. But regardless, this is just a useful tool to do. We can learn a lot about the speed of this object as it goes around a loop just by knowing its initial speed and its height in the loop. Now I'm going to show you a demo of something that I would normally do in person in lecture, but because it's online, I can't. So instead, I'm going to let the very famous Walter Lewin take care of it. So I'm going to stop sharing really quick, and I'm going to show you a video of another, show you a YouTube video. Hopefully everybody can hear this.
Now I want to return to the conservation of mechanical energy. I have here a pendulum. I have an object that weighs 15 kilograms and I can lift it up 1 meter, which I have done now. That means I've done work, MGH.
Hopefully you guys can...
Believe me. I've increased the potential energy of this object. 15 times 10, so 100.
The link is in the lecture, notes.
Then that will be converted to kinetic energy. If I
yeah, it's chopping my end too.
From 1 meter height.
Let me stop the share really quick. And yeah, I'll just paste the link into the chat. So then you guys can watch it. Why isn't it giving me it's just saying youtube.com. It's not giving me a URL. One sec.
Now I want to of mechanical energy.
Let me get the URL. This is it's a very scary demo to do, by the way. Okay, so I pasted the link. I'll give you guys like 2 minutes or so to watch, or 3 minutes to watch it. It's 3.5 minutes longer, so I'll just wait till 11:12 on my PC on my screen. But it's super scary to do. I've done it before in person. So go ahead and watch. Y final is the point that it's going through the loop. Yeah, YB is the height. We just chose a certain height that we were interested in the speed at. It was just a choice. We could have chosen any other YB. It's just that was the one that we were interested in. There's also a normal force in this diagram. However, we don't have to worry about the normal force because it never does work, because it's always perpendicular to the path taken. I don't understand. Would you have to use something else other than kinetic energy? I mean, like, energy conservation is always change in kinetic energy plus change in potential energy plus change in thermal energy. That's what energy conservation is. It equals the external work done. You guys should be watching the Walter Lewin video anyway. Sure. I mean, he has good stuff. He comes from MIT Open Courseware, so they have good stuff too. So I mean, like, there's plenty of material out there. Like, this is an intro physics class, and it's been taught the exact same way for the last 150 years. So you could find resources on literally anything that you don't understand for if you need extra help. All right, so I think that that's probably enough time to finish the video and have seen the near destruction of Walter Lewin's chin. So let's proceed. So he does trust it. I trust it probably slightly less, or at least I trust myself slightly less. I've only done it twice before. It was very scary both times. Right, so at the end of last lecture, I talked, and at the beginning here, I talked about the potential energy function for the gravitational force. And note that in order to have potential energy for a gravitational force, you need to include both gravitating bodies into your system. So notice that I said that the system that we're considering here is the car and the Earth, and that's because the force is between the car and the Earth. So in order for that to be an internal force, an internal work that's done, the Earth needs to be part of the system. Anyway, the next thing to talk about is the potential energy function. Potential energy function for the elastic force. I mentioned at the end of Monday's lecture that the elastic force is also conservative. And so it should indeed have a potential energy function. And so just as we figured out the potential energy function for gravity by basically looking at the formula for the change in work done work done by gravity and sticking a negative sign in front, we can do the same for the elastic force. So let's just consider a mass on a spring, and we're going to use this to illustrate how we find the potential energy function. Mass on a spring. All right, so in this case, the force, we know the formula for it. This is the elastic force. This is negative k times x minus x naught. I mean, it doesn't matter what you call the variable, but it is different here. Where in this case, we're going to, here, we have to assume that x naught is the equilibrium position. Yeah, well, there's no gravity in this. We're not considering gravity at all here, so gravity doesn't play a role. So we're just so we're going to, so this is the general formula for the elastic force. Note that these are general vectors that point in arbitrary directions. They don't necessarily have to point in the x direction. It's just the convention that we use. You could replace these with r's if you wanted to. And we're going to, just for the sake of easy computation, we're going to let both x and x naught be along the x-axis. So we really are just assuming that these are in the direction of the x-axis, just because it'll make the picture a little bit easier. So the thing to imagine is you have your axes, y and x, and you have your spring tied off, say, at the origin here. And so maybe here's our mass at position And so it has that the vector x naught or x there. And then the vector to the equilibrium position, maybe, which is at this location, would be x naught. That's all we're considering here. And so that means that x naught, or the x naught vector would be x naught in the I hat direction, and the x vector would just be x in the I hat direction. X is just the current position. That's what we're using as the label for the current position. So with this setup, the work done by the spring from, say, position A to B, maybe A to B is position, maybe it starts off at position XA and it goes to position XB or something. That would be an integral from XA to XB of negative k times x minus x naught dx. So the path that it's going from, it goes in the x direction. So the dl part is I hat dx. The coordinates it's going from is xa to xb. And the force is in the same direction as dl. It's in the I hat direction. So this is what the work that we get would be equal to. Remember that this is really equal to f dot dl. And here dl is dx I hat. And so you can take the dot product of f with that, and this is what you would end up with. Okay, but now we can just do this integral. This is just an integral we can do, right? So we would get 1/2 k times, let me put the right brackets, xb minus x naught squared minus xa minus x naught squared, square root. And so we could rewrite this as minus 1/2 k minus 1/2 k delta x diff. And I'm going to explain what x diff squared is. So this x diff, this is just a shorthand. So this is the x diff is the distance from the origin, or sorry, from equilibrium And so we could write that as, and dis, by the way, stands for displacement. It's just displacement from equilibrium. This is just x minus x naught with absolute values. And then we square it, and then we take the difference. So basically, this is the distance between the final position and the equilibrium, this first one I circled, and then you square that. And then you subtract off from it the distance between the initial position, or the square of the initial position, the difference between the initial position and equilibrium. So what does this imply? This implies, so that's what the potential energy would be. That means that we can actually write what the potential energy as a function of position is, not just the change in potential energy. It implies that the potential energy for the elastic force as a function of x. Now x here really refers to in the direction of motion. So if this had been upwards and to the right at a 45-degree angle, that's what x would refer to. So we have to be careful here. Like if I had, like, x is just a coordinate choice. Like I could have instead chosen to use these coordinates where this is y and this is x. And then I would have had my thing still tied off and it would have gone this way, right? Like this is just a coordinate choice. This x just represents, well, actually, we could even, we could actually just say that, how do I want to phrase this? Well, yeah, so assume that it's just x, or that it's just a distance from the equilibrium now, or a distance in the direction of equilibrium, but I'll explain how it can be generalized in a moment. So this is equal to 1/2 times, and remember, the potential energy function is the negative of the work. So that's why there was a negative 1/2 here, and there's not a 1/2 what I'm about to write. So it's 1/2 k times x dis. Oh, what just happened? Where'd it go? Okay, x dis squared plus u naught. That plus u naught always there because the difference doesn't affect it. Remember, I talked about this in the lecture that I posted. So by convention, we often set, so let me actually expand this. This is 1/2 k. And now we can actually just write x minus x naught squared plus u naught here. So by convention, and this is just a choice, like it's not a choice you have to make, but it's the choice that most physicists make. We often set that we often just choose that the elastic potential energy, I think the video is playing in the background, which will make my machine run slow, as a function of x naught rather, sorry, the elastic potential energy evaluated at the equilibrium position x naught, we just set that equal to 0. That's just a choice we make. And it's a choice we can make because there's a free variable in our potential energy function. So it would be like, you have some function like y equals 5x plus b. If that b is just some arbitrary variable, you can set it. You can use some condition on y and x to figure out what b should be. So it's just a convention. It's a thing that we're just doing to make our calculations easier. The end physics, the answer that we get at the end of the day for any of these problems would be no different if we had made a different convention choice. But this is just the choice that we make because it's easy. And so what that implies is that we have 0, which is equal to 1/2 k times x naught minus x naught squared plus u naught. And so that's just 0. And so this just implies that the choice that we make for that constant that we add to potential energy, we just don't add any constant at all. We just make that constant be 0. So we would get that the potential energy for the elastic force as a function of x is 1/2 k times x minus x naught squared. Now I said that I would generalize this, and so in fact, the true generalization of this formula. So this is a totally valid formula for potential energy, as long as you're restricting to just one dimension. As long as your spring is just going back and forth in one direction, that's fine. But if your spring can move, can like rotate, and if it can like pull into different directions, then you might want to generalize a bit. And so the generalization would require a vector position for, it would require you to specify the position as a vector of the equilibrium and the position as a vector of the yeah, it is actually. So I'm not even going to talk about this generalization because we're not going to need it. But the point is basically you'll just want to use the coordinate x to represent the direction that the spring is going in. Cole, it is meaningless, but you still have to make a choice. You still have to give it a value so you can do calculations. So we choose this convention. That's the whole point of choosing this convention. It's just a very simple convention. Right, so that's the potential energy function for, or a standard potential energy function for the elastic force. Now, I could have added plus 5 joules over here and it wouldn't change anything, but that's just not the choice you make. All right, next let's talk about thermal energy. So by the way, this formula that I just described will be super useful when you're talking about when you're doing some energy conservation problem that involves a spring. So keep that in mind. So so far I've given you potential energy functions for gravity and the spring force, which are really the most common ones that we're going to see in this course. So that would more or less fill out all of the possible potential energies you're going to see. There was one more term though in the energy conservation model that we haven't talked about. So the energy conservation was external work, which we understand, it's just the work done by external forces, equals the change in kinetic energy, which we understand, the change in potential energy, which we now understand, plus the change in thermal energy. And we haven't talked about the change in thermal energy. So let's do that. So we need to ask what thermal energy actually is. So thermal energy, or E thermal, is generated when a non-conservative internal force like kinetic friction, does work. Now remember, on Monday we actually went over how kinetic friction is not a conservative force. And so hopefully you remember that. So when a non-conservative internal force does work, that increases the thermal energy of the system. So the simple example that we will return to this example again later in the course is, let's say you have like a frictionless surface, like a frictionless table, really smooth table or something. And then you have a book that's sitting on top, but the top of the book is really rough. And then you start, and let's call that book B. And there's another book, the bottom of this book is really rough. Initially, B is stationary, and A is just overlapping on B, and then you push it, right? So you start off with A, with only A moving, with some speed VI, and this is the books right before contact. Or maybe like right as they make contact. So the idea here is you push the book, and so eventually, if the surfaces are sufficiently rough, book A will slow down as it or will lose energy, or not lose energy. It will push book B along with it, but it'll come to rest on top of book B, and then they'll just slide along forever. And so at some later point in time, we would end up with book B over here, book A sitting nicely on top of it. If it was perfectly calibrated, they would go the exact same distance or whatever. These are the books after contact. And now they're just moving with some speed. Now they're moving together because friction made them, the friction opposed the motion, the relative motion between the two. And it opposed it enough that it just stopped the relative motion. So now they're just sliding along together. So book A was on top, it was pushed, and then it slowed down because of the rough surface between A and B. But it pushed B along in doing so, because friction is has an equal and opposite force pair. And so then they just are together moving to the right. So in order to do an energy analysis of this type of problem, we need to know a few things. We need to know things about distance traveled. So let's first look at let's look at book B. Book B will have traveled a distance, call it delta xb. Book A, on the other hand, will have traveled further. Why does this keep happening every time during lecture? Book A will have traveled a little bit further. It will have traveled the distance of the book, right? The distance that like the distance on book B that it traveled. So let's consider the system is book A. In that case, the work or the external work, because there's no internal work to book. By the way, we're neglecting gravity like we usually do in these situations. The external work done is negative. And the reason we know that is because book A starts off going at some speed, and then it has to slow down. It slows down because it must make B speed up a little bit, right? So it has to lose, some of its energy has to go away. So this is because the change in kinetic energy is negative. And so the work energy theorem tells us that if the kinetic energy goes down, then the work done has to be negative. If the system is book B, on the other hand, then the work is positive. It starts off at rest, and then in the final condition, it's moving, so its kinetic energy increases. So it has a change in kinetic energy that's positive. So what happens if the system is book A and B? So in that case, the friction that was the source of external work when we were just considering either book A or book B, because the friction was coming from the other book. In this case, now the friction is internal to the system, right? Because the friction is just between books A and B, and those are both part of the system. So we can figure out what we need to include in our energy conservation equation by considering the work on both book A and book B, and then adding them together. The work on book A is equal to, well, it's equal to the negative of the magnitude of the frictional force times delta XA. So here, F equals magnitude of friction force. So we know it should be negative. The magnitude is positive. Things in parentheses. That's because it's a B/C, sorry, because. Right, sorry, it's an abbreviation I use. So F is positive. We know delta X is positive because it's just the distance. And so and we know that the work should have magnitude just the force times the distance because they're in the same direction as the distance traveled and they're constant and so on and so forth. And so we just stick a negative sign in front. So this is the work done on book A because we know the work is negative, we know the magnitude of the force, we know the distance traveled. The work on book B is similar. Doesn't friction only No, because so friction acts for the entire distance it travels. The work on book B is positive. It's F times delta XB. The work is, or the friction is being applied the entire time that it's moving from the initial to the final position, and it has magnitude F. In this case, it's pushing it in that direction. We know the work is positive or negative because we know the change in the kinetic energy. We know how the speed changes, so we know things about the change in kinetic energy. Hence, we know how the work is positive or negative. So in this, and we know that these magnitudes are the same because the friction forces are equal and opposite. That's another good way to see it, Hassan. In the case of book A, the frictional force is opposing it moving forward because it is trying to slow it down. So the work would be negative. For book B, the the friction is pushing it forward in the direction of motion. So it acts to speed it up. So the work is positive. So the work on both books then, just by adding these two together, is F times delta XB minus F times delta XA. So it's negative F times delta XA minus delta XB. Delta XB. And this number here, delta XA minus delta XB, this is the distance that book A slid across book B. I.e., it's the amount of it's the distance in which they were both rubbing. Like it's the amount of it's the amount that book A slid on book B. So what does that say? So that says that the work on it's either the length of B, or maybe it doesn't completely overlap on B, or maybe it overlaps a little bit more on B. So let me just so it's not, so I'm not like lying to you. Maybe it only overlaps a little bit or something like that, right? The point is it's just the amount that it slid. It's the extra distance that it covered. So the work on both books can be written as negative F times delta X rubbing. It's the distance that book A was sliding across on B. And that has to be less than 0 because this is positive. So isn't the friction force applied on B by the A block? It's opposing, remember, friction opposes relative motion. All it does is it opposes relative motion. What that means is if A was going to slide on top of B, the friction acts to prevent A from sliding. But then friction has an equal and opposite force. So there's a friction force from A acting on B, pushing it in the opposite direction, pushing it to the right. Remember, friction has a Newton's third law pair too. So you always have to consider that. And think of it this way. From A's perspective, B is the one that's moving. And so B needs to have a friction force pushing it to the right to stop it from moving relative to A. These reference frame things actually turn out to be kind of handy. So the whole point is that the internal work to the two book system is negative because of friction. So because there is no external friction, in our two book system, and remember, you can just kind of choose whichever system you want. Our energy conservation equation looks like 0 equals delta KE plus delta E thermal. And we know that this is equal to delta E thermal is equal to the negative of the work done by the work done by internal non-conservative forces. This is minus the work done by both books, or the work done on both books, the internal work done on both books, which tells us that the change in kinetic energy is equal to the work done on both books, the combined work on both books, and that's less than 0, which tells us that the final kinetic energy is less than the initial kinetic energy. So the whole point of this exercise was to indicate that when you have a non-conservative force internal to the system, the kinetic energy goes down. It has to go down. And this is the total kinetic energy. So even though book B starts moving, book A slows down more so that the sum total of kinetic energies of both books combined is less than the initial kinetic energy of book A. So the question is where did that kinetic energy go? Where did that extra or that lost kinetic energy go? And the answer is kind of built into the name. It goes to increasing the temperatures of the well, it potentially goes towards increasing the temperatures of the books. Now, it could also, there are other places that thermal energy can go. It can also go towards producing sound or producing light. All of those things are thermal energy. Basically, sources, energy that can't be easily captured often gets lumped into kinetic or thermal energy. When you have a non-conservative force in the system, kinetic energy goes down. Generally, yes. If it's friction, sorry. There can be non-conservative forces that also increase the that increase your energy, but those don't show up in real life a whole lot. Yeah, so the whole point is that kinetic energy, maybe it produced sonic energy, maybe it made a loud sound. So the energy of that sound wave would be completely equal to the energy lost by the kinetic energy lost. So that yes, indeed, it does all cancel out to 0. So there is a notion that this energy that's produced, or the energy that's produced in the form of thermal energy, is not retrievable, in the sense you can't take thermal energy and convert it back to kinetic energy, at least not without expending more energy. And so there's good reason for that. One of the reasons is that molecular motions are generally random, and you'll learn about why that happens in 9B next quarter whenever you take it. Another explanation is that you have orderly macroscopic kinetic energy, i.e., all of the atoms in the book are moving at the same time, which is converted to random microscopic kinetic energy. So the atoms in the book are now all moving in random directions, and you can't go from disorder to order as easily as you can go from order to disorder. That's that has to do with entropy. And again, you'll learn about that more in 9B. Hannah, that's exactly what motion is. That's exactly what macroscopic motion is. There is a discussion of microscopic and macroscopic models of energy that you guys can read about more in section 3.5 in the online textbook. So I highly recommend you take a look at that. No, atoms just do grow legs. I mean, I have a degree in physics. You should trust me on this. Just believe me, right? So the next thing to talk about is how forces relate to potential energy functions. We know forces relate to work, and work relates to potential energy, but not directly. So there is indeed a way to relate force to the potential energy function more directly, and it just takes a little bit of work. So we're going to do that. Force and the potential energy function. So we've talked about the potential energy function for two forces that we understand well, gravity and springiness. But now we have kind of a way to produce. Now we have a way to discuss conservative forces in a more general fashion. We just write down a function, a potential energy function, and then we say that's the potential energy function. Now what's the force for it? Like what would the force be if that was that force's potential energy? So and that's what we're going to want to get to. Now, when conservative forces are involved, we don't necessarily need to compute work directly in order to apply the work energy theorem. That's the whole point of potential energy functions. If you know that gravity is involved in some problem, instead of computing the work and then doing an integral, computing the work, and blah 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 blah, you can just use the potential energy function instead of computing the work, and it's really really easy. You just like plug in two values and then take the difference. We want to know what the relationship is between force and its potential energy. So we're going to consider a small amount of work. We're going to call it dW. So remember, when you put a d in front of something, usually it just makes it really small. Done on done on an object by a force. So we've done this before when we talked about power, by the way. So dW is just equal to F dot dl. So if F is just some arbitrary force, it has a component in all three directions, this would be equal to F, the x component of the force in the I hat direction, plus the y component of the force in the j hat direction, plus the z component of the force in the k hat direction, dotted into the path. Now the path could be a little bit in the x direction, it could be a little bit in the y direction, or it could be a little bit in the z direction. Could be any of those, right? And so when you take the dot product, you'll get fx dx plus fy dy plus fz dz. So that's what a little bit of work looks like for a general force. Now, if this is the only force that's on the system, is only force on the system. Sorry, I need to write this down so that it actually logically makes sense. Then the work energy theorem tells us that that small amount of work that's done, that's equal to a small change in the kinetic energy. Now, if the force is conservative, then the small change in kinetic energy is instead, or is balanced out by a small change in the potential energy. So if you slightly decrease the kinetic energy, that means that you slightly increase the potential energy. So these added together should be zero, the changes. And so that implies, that the small amount of work done is equal to the negative of the small change in the potential energy. Now, this shouldn't take you by surprise because we know for a conservative internal force, the potential energy, the change in the potential energy, the work done by that internal conservative force is the negative of a change in the potential energy. This is just the differential equivalent of that. So now we're just going to specialize to make things easier. So now we're going to suppose that the force is only in the x direction. It's just f sub x in the I hat direction. Simplifying our problem. So then f sub x dx, because the other terms would be zero, because there is no f sub y dy, there is no f sub z, because those are the components that are zero. So f sub x dx then would have to equal, so we're using this relationship and this relationship combined with this relationship here to get us that f sub x dx is equal to negative d dE. It's equal to the negative of a small change in potential energy. And so we can cheat, do some rearranging that you're typically not allowed to do, and you find that the force in the x direction is the negative of the small change in potential energy divided by the distance traveled. Or, put another way, it is the negative derivative of potential energy with respect to x. Now, from now on, just as a notational thing to make things easier, we are going to use the letter U, capital U, for potential energy from now on. So instead of having PE sub G, we will have U sub G. You smell correctly. Right. So we need to actually talk about partial derivatives here, just for a quick moment. And their partial derivatives will be outlined in the textbook online as well, so check that out. But just as a quick aside, a partial derivative is super easy if you haven't seen them before. It's just a regular derivative. And that's basically it. So you, that's a no, thank you, I guess. A partial derivative is a partial derivative is basically just a way of taking a derivative of a multivariable function. Exactly, yeah, you treat the variables, the other variables, as constant. So if we have, say, let's actually use u. So if we have u of x and y, i.e. it depends on two positions, maybe it depends on your x and y axis, then the partial derivative, which we write with curly d's, partial derivative with respect to x, would just be the derivative of this thing. It would be, well, let's say that this is x plus y. This would just be 1. Okay, terrible example. There's a better explanation given in the textbook. But the point is you treat so du dx is equal to the derivative of u of x and y as if, or with respect to x, with respect to x. So you take the derivative with respect to x, and then the important part is as if y was constant. So all you do is you just pretend that the other variables in your function, you just pretend that they're just numbers rather than variables, and then you just only take the derivative of the thing that you're interested in. So, so enough with that aside. So from the argument above, we actually have that f sub x, the force in the x direction, is the negative partial derivative of the potential energy function with respect to x. F sub y is the negative partial derivative of u with respect to y, and f sub z is the negative partial derivative of u with respect to z. Now, if u only depends on x, partial derivatives are just normal derivatives where you treat the other variables as constants. So I'll give you an example in a minute. Actually, if we have time, I will. Yeah, I'll try to get to the example. I might run a few minutes over. Yeah, I'll give you an example, and it'll be super obvious. Like partial derivatives are not scary. They're super, super simple things. They just have a scary name. So the point is from that argument above, where we just assumed that the force was some general thing, and then we just used our relationships about conservative forces and work and so on, we get that each of the components of the force can be written in terms of partial derivatives of the of the potential energy function. And so, in fact, the force, the most general force, can be written as the partial derivative of u with respect to x in the I hat direction, minus the partial derivative of u with respect to y in the j hat direction, minus the partial derivative of u with respect to z in the k hat direction. I promise they're just as easy as regular derivatives. So put another way, there's another notation that people use. F we would write as the negative gradient of u. Now, this is just a notation thing. This gradient, as an operator, is just I hat partial with respect to x, plus j hat partial with respect to y, plus k hat partial with respect to z. Now, don't worry about what this means. Don't worry about what this means in particular. You'll see it more in Math 21D, I think. But it's just a notation that you might see elsewhere. So if you see it, this is what it means. It just means you do these things on the stuff to the right, and then it spits out what you want. So the important point is that this method of finding the force only works for conservative forces. It only works. That like there's no way to get a force from there's a difference between those. There's no way to get a force from a potential energy function for a non-conservative force because there is no potential energy function for non-conservative forces. So as a useful sentence, which is a true statement, a force, so this is another characterization of conservative forces. This is useful. A force is conservative if and only if It can be expressed as the negative gradient potential energy function. Sorry, it's cutting out. I don't intend for that to be the case. So this is just this is another equivalent way of figuring out whether a force is conservative. If you can express it as the gradient of a potential energy function, then it's conservative. If you can't, then it's not. So, okay, so I guess I'll have to end it for now because we're over time already and I don't want to. So what I'm going to do is I'm going to end the recording here